Welcome to In 5 Minutes. We take problem on temperature stresses. A problem statement is a composite bar consisting of steel and aluminum components as shown in a figure will be given, is connected to two ends at a temperature of 60 degrees centigrade. Find the stresses in the two rods when the temperature falls to 20 degrees centigrade. Again it is for two cases, if the ends do not yield and the ends yield by 0.25 mm. So this is the figure which is given in the problem. We have steel bar and aluminum bar which is connected as shown in the figure. Steel is of area 250 mm square, whereas aluminum bar is of area 375 mm square, and the length of steel and aluminum bar is 800 mm and 400 mm respectively. Now it is being given initially the bar system, steel and aluminum, is at temperature Ti equal to 60 degrees centigrade. Now what they have asked is when the temperature falls to 20 degrees centigrade, so we have delta T is equal to 20 minus 60 as minus 40 degrees centigrade, meaning that the steel and aluminum bar system has been cooled by 40 degrees centigrade. So when that happens, we have been asked to find the stresses in the two rods, that is in steel rod and aluminum rod, for two cases. In the first case, when the ends do not yield, that means the two ends are rigid, whereas in the second case the ends yield by 0.25 mm. Now as we know, as the steel and aluminum bar has been subjected to cooling, both the steel bar and the aluminum bar will try to contract as shown in this dashed black lines. So this composite steel and aluminum bar will try to pull this ends towards it, so that the total deformation of steel and aluminum bar is contraction. So in the second case they have asked that due to this pull, if this end yields by 0.25 mm, meaning that this end yield towards this direction by 0.25 mm, so that your delta L, total deformation of composite section, is minus 0.25 mm. What is the corresponding stresses developed in this steel and aluminum? We first write the given data of steel and aluminum bar in the problem. We have ES is 2 into 10 to the power 5 Newton per mm square. EA, which is Young's modulus of aluminum bar, equal to 0.7 into 10 to the power 5 Newton per mm square. Alpha S is equal to 1.17 into 10 to the power minus 5 per degree centigrade, whereas alpha A is 2.34 into 10 to the power minus 5 per degree centigrade. And the area of steel bar and aluminum bar is given as AS is 250 mm square, whereas AA is 375 mm square. And in this problem we have been asked to find the stresses in steel and aluminum bar, sigma S and sigma A, for two cases. First, when the ends do not yield, that is delta L is equal to 0, that is for this case. And in the second case, when the ends yield by 0.25 mm in this direction, so your delta L is minus 0.25 mm, since your steel and aluminum bar is both contracting. So we start with the solution. We take the first case, that is when ends do not yield, that is delta L is 0. Now we can see that as your temperature delta T is decreased by 40 degrees centigrade, both steel bar and aluminum bar will try to contract as shown. Now since the ends do not yield, this end or support will try to elongate or pull this steel as well as aluminum bar towards it, so that there is a tensile load or tensile stress developed on both steel and aluminum bar. Now since the steel and aluminum bar are in series, this tensile load P will be equal on steel as well as aluminum bar. So now we write the static equilibrium equation first, which is our force balance equation. So we have the load developed in steel PS is equal to the load developed in aluminum. So we have sigma S into AS is equal to sigma A into AA. Now upon substituting the values of AS and AA, we get sigma S multiplied by 250 is equal to sigma A multiplied by 375. So we get sigma S equal to 1.5 sigma A. Let this be equation 1.